and we move to the next speaker in our program. And this is, of course, Dr. Andrea Lausi, the scientific director of the SESAME synchrotron, where the Beats beamline will be constructed. And in the way of introduction, Dr. Andrea Lausi is a steering committee member of the Beats project, as well as leading the work package 6 beamline assembly and commissioning. And he got the laurea degree in physics at the University of Trieste in 1991, with a research focusing on phase transition in two-dimensional systems. Main scientific activity of Dr. Lausi is in the field of X-ray scattering, optics, and methods, including high-pressure powder diffraction, atomic X-ray holography and diffuse scattering. And Andrea has extensive experience in the science programs of synchrotron light facilities, having worked at Elettra Syncrotrone Trieste in Italy since 1996. And Dr. Andrea Lausi also has long-standing experience in science communication. He was a member of the communication task force of Elettra and the person responsible for the Elettra content. In April 2019, he was appointed chair of RISE. RISE stands for Research, Infrastructure, Communications and Engagement. And this is a working group of the ERF AISBL, which stands for Association of European Level Research Infrastructure and Facilities. So it's my pleasure now to give the floor to Dr. Andrea Lausi, who will be talking to us about Beats in the context of SESAME. Andrea, please.
Thank you, Kirsi. Thank you, everybody. Thank you to all the convenees, all the organizers. And what I must say also is that I am also the new scientific director of SESAME. I am here only since March, and I think that the word March tells you what I have encountered since I am here. In the very first days, I was already planning a physical visit to Qatar, which obviously could not have taken place until now. So really, really happy to be finally, at least virtually, with you. And what I will speak today is essentially, I will give you an introduction of what a synchrotron is, what a synchrotron source is now, and on something about the history and the status of SESAME in particular. So let me share my screen. And so in the first slide, what you see is the building of SESAME lying in the wonderful hills north of Amman. And this is the building which hosts the storage ring, which is SESAME. It is where we produce soft X-rays, hard X-rays, infrared radiation in order to study matter. So to make a bit of a history of these kind of facilities and of the use of X-rays, which has given so much insight about matter, we remember that these X-rays, these mysterious rays, were discovered much time ago, but in a very short time, science found also a way to use them, apart from some very first funny trial. I remember an article in 1907 about the color of X-rays. It was a German article of a scientist telling that blue, because if you put the eye to a tube producing X-rays, your eye at a certain point tells you that you are seeing something blue. And most probably don't see much more for the rest of your life. So that was a field of research that was abandoned quite early. What is the color of X-rays? Instead, what went on quite long is the use of X-rays of various wavelengths, from soft X-rays to hard X-rays, to have information about matter, positions of atoms, chemical nature of samples, and so on and so forth. And application after applications, this required brighter and brighter sources of radiation. So starting from the Coolidge tube, which every department of chemistry has in its basement, and every hospital has in its radiology departments, has brought X-rays everywhere in the world. But it has been also found out after the end of World War II that this radiation could have been produced also by moving electrons, accelerating electrons at a speed very near of the speed of light. And that the light produced in this way was much better in terms of many properties with respect to what you can do with the laboratory source. Accelerators were already there. They were built by physicists to explore gliders, to explore the subnatural, the inside of the nuclei. Well, then material scientists started use of these facilities, which was so successful that nucleated the use, the construction of dedicated machines. So in the 70s, the first synchrotron center started to be built for research, and this went through a process of development and which brought us to our present third and maybe fourth generation of facilities. So what are the things that make these kind of sources so special with respect to what you can have in a laboratory? Many properties, which are listed here in red with some comments, but essentially two of them. The wide spectrum, which is available, and the brilliance. By brilliance, I mean the number of photons which you can obtain per second, per millimeter square of the source, in a millirad squared of the beam divergence, and for 0.1% of bandwidth. Complicated notion of brilliance, because it is a number that gives you a feeling already. It's a figure of merit which lets you understand more or less already, just looking at these characteristics of the source, more or less how many photons you will be able to have on a tiny spot in your sample at the end of the instrument that you construct to tame and to tailor this radiation to your experiment, which is the called beamline, of which we are speaking today as beads, for example. So, about the spectrum, as you see, the electromagnetic radiation that you can obtain from a synchrotron spans several decades and goes from microwaves through infrared, crosses the visible, which is that very tiny part of the spectrum, goes into ultraviolet, vacuum ultraviolet, soft X-ray, and up to hard X-rays in energy, or down in wavelengths to below the Ångstrom. And this makes them exceptionally flexible sources. So you can build a ring, and depending on how you manage some details of the magnets that you put in there, you can obtain very different sources for the very different kind of experiment measurements. What to build then? Okay, it's a natural phenomenon after all. It's nothing. It's something which exists in nature. On the left of your screen, you now see the Crab nebulae as seen through a X-rays telescope, Chandra, and you see that the result of the explosion of the supernova which created the Crab nebula, there is a lot of charge which is running at the speed of light, which throws in our direction X-rays. Without being so dramatic and so far, we can build instead machines, facilities in which we keep electrons in orbit practically at the speed of light, 0.99999 and several 9% depending on the energy, which could be goes normally between 1 and 6, 7 giga electron volts. You keep them in orbit, and then by being in orbit, as already Axel has remembered, at every curve they do emit electromagnetic radiation of various kind of wavelengths. So a synchrotron radiation facility nowadays is made in this way. You have a injection system, which can be a linear accelerator or a linear accelerator plus a booster, which is a real synchrotron. Synchrotron gets its name, it's an accelerating machine. It gets named by the fact that at every turn you increase the energy of the particle inside, which you are accelerating. If you do this, you obviously have also to increase the field of the magnets in order to keep the same orbit. So in order to keep the same orbit, you synchronically increase the magnets, hence the name synchrotron. So you either have a LINAC or a LINAC and booster, and from there you get bunches of electrons into a vacuum ring where actually you stop increasing the energy, but you just keep them in orbit. This is called a storage ring. 99% of the machines around are storage rings now. And these are polygonal objects, so straight sections, bending magnet, straight section, bending magnet, and they keep the electrons in orbit, in round orbit. At each bending magnet and along the path, at each other set of magnets, radiation will be emitted and will be collected and used for experiments, which means that at every turn, these electrons will lose energy. So you need a radio frequency cavity which restores at every turn the energy of the electrons. So the name of the game is just to keep them in orbit and circulating them as long as possible at the speed of light. Okay, so the various kind of that you find in these machines define the kind of source that you have and give you one of the stories of success of synchrotrons in the past 60 years, which is this always famous graph of the brightness versus time, the very famous Moore's law. Yeah? Moore's law is the history of success of modern industry, the number of transistors which double every 2 years. That is the green line. And on the other, on the left of it, you see the line which shows you how much the brilliance has been increased by building better and more performing rings and magnetic devices inside the rings during the past 60 years. So you see that going from X-ray tubes, which date, as you know, from much before, X-ray tubes are a very violent way of X-rays. You know, you just smash electrons to a metal target and you shake up electrons. They return to their core positions by emitting X-rays. This goes in every direction. The brilliance is very limited. Then, instead, if you do, and that was the secret of success of the first uses, or the first generation, if you have a bending magnet where electrons are moving at the speed of light, you get a much, much higher brilliance. You go up by 12 orders of magnitude already. And this makes it already interesting to build machines and optimize them for this purpose. And so you get second generation machines, which synchrotrons which are built for producing X-rays. Then to go to the third generation, if you introduce between the bending magnets, in the straight sections between the bending magnets, set of zigzag magnets, which if the name of the game is make the electron bend, then you can build many bends one after the other. And in this way, you get a wiggler or an undulator. The wiggler will be simply the reproposition of the bending magnet effect several times. So you increase your intensity by the number of poles. If instead your undulation is very small, then you have interference between what is emitted at every zig and every zag, and in this way you get the key apparatus third generation source, which is a undulator, where the intensity is proportional to the square of the number of poles. Or you can do it even more and go to fourth generation machines with free electron lasers, in which you build an extremely long undulator, which then you are out of the paradigm of round machines. You just put a long undulator at the end of a linear accelerator. And in this way, you have the effect that from the beginning of the undulator, electrons start emitting. They travel at the speed of light, so which means that they travel together with the radiation they emit. And starting from thermal noise, then you have interference between the electron and the field emitted, and you have bunches which regulate themselves to be all in phase, and in this way you have a multiplication. So you have interference between the light emitted between two different electrons, and at the end you multiply by the square of the number of electrons in the bunch. But number of electrons in the bunch is 10 to the 10. So you squaring that number, you get an going from the synchrotron to free electron lasers. Okay, once you have built this machine, you are only halfway to the experiment. What you need to do is a beamline, that is the optical object which allows you to tame the radiation and tailor it to the experiment. So for In general, what you will have is something containing pipes with mirrors, monochromators, slit systems, shutters and stoppers for safety and for closing, all under vacuum, and bringing the beam down to the at the end. So, what happens when you decide in your country or in your region to build a synchrotron, to build an instrument like this, which is, as I remembered, a very, very flexible machine. So, the day you have finished, you obviously first build the machine. So the day you end the machine, you have a huge hole, empty, ready to host beamlines. And if you go on and on and on with this, you end up in a situation similar to this is the little synchrotron in Berkeley. And as you see, it is a totally crowded space with experimenters, so on beamline A, B, C, D, E, F, G, etc. You find people dealing with batteries, dealing with stress and strains of materials, dealing with cultural heritage samples, dealing with any kind of science, and they are so close. They do also interact day after on a daily basis. So what you have is really a mall, a cultural science center, evolves continuously and adapts to the scientific case around it. It's like in a way it's just like the market. The market is not made by the producers. The market is made by the consumers. So in our case, the synchrotron is not made by the beamline scientists. It is made by the users, as well as the synchrotrons. Inside the synchrotron, there is a community which interacts. The way synchrotrons interact between them, among them. And so since a few years now, it exists the League of European Accelerator-Based Sources, LEAPS. And SESAME is, since 2 years, the first associate member of this league. And you see the numbers around here. We are speaking of a community of 40,000 researchers all around Europe and also the Middle East who do use this machine to produce their science. SESAME is a story of visionary people in this scenario, in this international thing. So I am somehow proud. It started in my hometown, Trieste, which maybe some of you know because of the International Center for Theoretical Physics. So, and this is where it actually, the interaction for the onset of this source in the Middle East started with the first document signed and then looking for a place and then starting defining how the machine could have been done. The first thing was finding a place, and that was Jordan at the end, in this, in this magnificent place where I live, which is Allan, northeast of Amman. Yeah. So then the members, the members involved in the construction of SESAME are Pakistan, Iran, Palestine, Turkey, Cyprus, Israel, Jordan, and Egypt. They all join forces in order to build this machine in a consortium, in an international institution which has been modeled after CERN. So we have members and we have also observers. The role of the observers is to help, to also to be sometimes economically involved or to foster forces outside of the members. The original idea was, and this is something I want to stress out because the story was beautiful, after all, that it stuck with us, that the German light source BESI 1, which was a source built in the 80s, was to be disbanded, and German scientists proposed to use it to build SESAME. But this is not really a good idea because you are not providing an up-to-date machine if you start from an old one. So this idea was abandoned, and BESI 1, part of it was used for the injector, for the booster of SESAME. SESAME is a totally new third-generation light source and has been built only to be SESAME, not as a refurbishment of a previous machine. So, as being a synchrotron radiation source like the one which I have described before, now we can observe how it looks like in the map. So this is LINAC and booster. Here we have the microtron and part of the old BESI 1, which is now completely refurbished and is our booster. From the booster, electrons are injected into the main ring, which is this one. These are the radio frequency cavities, and these are the bending magnets and the straight sections between bending magnets where you can put insertion devices. Yeah, you know, we physicists don't have much fantasy for names. So the general name for these devices, which you insert wigglers and ondulators in the straight section between bending magnets, are called with the general name insertion devices. And so here you have the various beamlines. There is an infrared beamline, which is already operating, X-ray fluorescence and X-ray absorption fraction beamline already built, a material science powder diffraction beamline. Here will be beads. As you see, beads will be the longest instrument of SESAME. It's 40 meters, and HESEP is here as coming soon as a soft X-rays installation, which will have also a Turkish branch line here. So there will be two beamlines here, actually. I will go through just a few images just to see you which kind of difficulties we had to address and how we overcame it and what it looks like in real life. So this is the radio. This is a mirror chamber being put in place. We are the only one, the only synchrotron which is completely powered by solar plant, and these are the phase 1 beam lines. Beats is among them. This is how we work. But of this second part, I will speak more tomorrow when I will introduce how to make a proposal and how to become a user. This is the current per day, and this is a show of the many proposals from the many countries that we receive every 6 months, 1 year, 1 year and a half, depending on how much Corona is. But here we are already in the presentation of tomorrow. So I think that I stop here, and thank you very much. And we will check in again tomorrow, but with the procedure how to apply for beam time at SESAME.
Thank you very much indeed, Andrea. Of course, the presentation of Dr. Lausi tomorrow will be of direct interest to everyone who is wishing to use the BEATS beamline in the future, or indeed any of the other beamlines that are already operational at SESAME. So thank you for this talk, Dr. Lausi. Are there questions for Dr. Lausi at this point? Any questions in the chat? No? Anyone who would wish to comment or query at this point? I was very pleased to note in your table, while you're all thinking about whether you have questions or queries to Andrea, I was very pleased to note in the table for the beam times allocated, I think I noticed there Qatar, Andrea. Can you tell us a little bit more?
Yes, for the first time here, we had a request of beam time for XF measurements from Qatar, and the experiment has not yet been performed because of the status we are in now. It will be, I will explain it tomorrow, but we are now using what is called mail-in. So since users are not able to come because of restriction in traveling, they are sending samples. So wave after wave, we are inviting scientists to send us the samples, and then our beamline scientists, together at the phone or in Zoom conference with the users, measure them and go on.
I think, excuse me, I think the researcher from Qatar, she's joining us also this session. And she told me that she's looking to be personal because she has to do in situ some measurements, not by sending samples. So some of her samples should be prepared in situ. So.
Okay.
So that's why she is looking to do it hopefully by next March or sometime, which is something extra.
It will be March. We might be optimistic as I see it now, how the planet is behaving. Yeah. But yes, a certain amount of users will need to be here. Yeah. So there are not every. This mail-in process is not for everybody. It's not not everybody can accept to do it. Someone needs to be here because the preparation of the sample is sensible, and so yes, okay. If this is the case, even more, she will be most welcome to be here.
Yeah.
Thank you, Dr. Grauber, for this update, and it's really very pleasing to hear that there is growing interest from Qatar to use SESAME, this science facility, in our region.